Okay, thank you very much to everybody to stick around this Sunday morning for this presentation about not the solid part of the Earth, but more on the origin of the atmosphere and the hydrosphere. I will make a presentation concerning the two because the two are related. It is the story of how the atmophile elements arrive on Earth. And first of all, I prepare a small slide to explain, as has been done before, who I am and why I am here. So I'm a rare gas or noble gas geochemist. They are becoming rare and rare. People are doing the geochemistry, isotopic geochemistry of noble gases. Presently, I'm director of Geotop. That is one of the largest research facility in Canada dedicated to isotope geochemistry. I was in another life an astrobiologist, or I strongly believe to be that. And my work, I am known in the community because I became a long time ago a specialist of nitrogen isotopes to use replacing not carbon isotopes. Everybody uses carbon isotopes, but nitrogen isotopes in ancient rock to understand, to find the trace of life or past metabolism acting in all the time. Now I'm working mostly on water, mostly in groundwater. That is the most precious resource we have on the Earth. But I also work in deep carbon, diamonds, volcanism. It looks not related with astrobiology, but you will see during this presentation that also this stuff is concerning. So the last question, why I am here? Muriel asked me, I have no choice. So this is the reason I'm here. Okay. So everybody know this figure is this photo is come from one of Apollo mission, and you see our planets. They have two important things that make looks for an astronomer from outside uninhabitable planets. Relatively thick atmosphere, of course not thick and dense like in gaseous planets, and a global oceans. And this is very important to have these two features on this planet, particularly oceans, water, because of course water is important for life and for also if there exists organisms that can survive without water. Main organisms need water to reproduce, to do metabolism. And of course, water is one of the best solvents we have because it is a polar molecule, and so we need this for several biological reactions. So the summary of my talk, first of all, especially for students, a little bit of vocabulary, and then I will present some few slides on the historical view on the Earth atmosphere from Aristotle to Ruby in 1951, let's say maybe also in 70, Armand Craig, because it's very important because we had a specific view. We stick with a view on where come the volatile elements, and this oriented all our research until cosmochemistry entered the scene, and with the isotopes we can change this view. Yesterday people speak normally that we know that water can bring from asteroids, etc. But 20 years ago it was not the case. The first paper speaking about the late Veneer is the Dreyfus and Wank, 1982 or 1983. So the evolution of the thinking on how water and the gas composing the atmosphere arrive on Earth is quite recent one. So we will discuss about the source of these atmosphere elements in terrestrial atmosphere, hydrosphere, solar chondritic or cometary sources using isotopes, mainly noble gas. This is my specialty, and the hydrogen isotopes for water. A few exciting discovery done by Rosina, the the instrument on the Rosetta mission, on the Chury comets. They give us some strong answer, but also new challenge. And this is important to have this kind of mission that challenge us, and we have to start again thinking and improving our models. And a general evolutionary model, you will see that I am very bad in drawing, so I'm not a really good geologist that should be very good in drawing. So I make some small animation to explain how it's work and how atmophile elements arrive on the Earth. So first of all, a little bit of vocabulary. So I will discuss on how these elements arrive on Earth. So the atmophile elements for geologists, we use the geochemical classification, so it's based on their behavior. Are the elements, they are extremely volatile and they form gas or liquids at the surface of the Earth, and they are usually concentrating in the atmosphere and the hydrosphere. This is hydrogen, carbon, nitrogen, noble gas, namely helium, neon, argon, krypton, xenon. Radon is just put there because it's a noble gas, but of course radon is not stable, it's a decay in a few days, so it's not really important in the general picture. And then I put oxygen. Why? Oxygen is not an atmophile element. Normally oxygen is related to silicates. On the rocky planets, oxygen is with silicate. Why is in our atmosphere? Because our present day atmosphere is what is called an habitable atmosphere. Our life-sustained atmosphere means organisms play a role to make this oxygen concentrated in the atmosphere. But there's been a very exciting discovery on Chury that we have molecular oxygen around this comet. So what the hell is doing molecular oxygen around a comet? So we should ask us, see if we understand everything about atmophile elements, and maybe oxygen could be also an atmophile element. Sometimes people, especially in papers, speak about volatile elements. It's not exactly the same things because in the planetary science classification, the volatiles are all chemical elements and compounds with low boiling point, less than 1,100 Kelvin. So there is not only the classic volatile atmophile like carbon, nitrogen, noble gases, but also halogens or some elements that is concentrated on the planets or moon cruise like potassium, rubidium, sulfur, etc. So there is a difference when we speak between atmophile and volatile elements. Okay. So I will present several slides. I speak about noble gases. Noble gases are on the last column of the Mendeleev periodic table of classification of the elements. And you know that the elements are on this column. They have their electronic configuration that is full, so they are chemically inert. And this is one very important feature of noble gases. So why noble gases are interesting? Not because it's my job to do them, but it's because they are atmophile elements. They are quite rare, so if you search a tracer elements, you need a rare. They are rare in the different reservoirs to be used like a tracer elements, and especially they are chemically inert. So their abundance and isotopic signature are related to the original cosmic or terrestrial reservoir, and only physical processes can fractionate them, not chemical one. So they are among the best geochemical tracer of atmophile sources in the solar system. They are so powerful they can also destroy Superman, as kryptonite do. So when we speak about noble gases, we have two components. One is called the primordial component. It's there since the beginning of the solar system. On the Earth, this primordial component can be found in the atmosphere or on the mantle. What about the core? We don't know. It's, sometimes when we don't know where is some elements, we put always in the core. I call the core the waste of geochemists. geochemists, when they cannot explain something, they say because it's trapped in the core. So maybe core have also some noble gas. Well, we don't know. It's possibly have some nitrogen. I will show you later during this presentation. And the sources are solar, or what is called planetary components. So what is coming with the comets, or is coming with meteorite, which is carbonaceous chondrite or other type of chondrites. And then we have the radiogenic component. This is less interesting for us for this talk, and is concentrated in the crust in the mantle, is derived from nuclear reaction like decay uranium that produces the famous helium-4 isotopes. So between the isotopes that we'll discuss during this presentation, we have the helium-3, the neon-20, argon-36, krypton-84, and xenon-130. I put in parentheses helium-3 because the helium-3 is the only isotopes that we are sure 100% that the helium-3 that is presently on the Earth have a solar source, while the other is mostly planetary. There is a lot of discussion about the origin of neon. Some say that some neon is a solar, somebody know. We can discuss this later if you want with a few slides. And then a few terminology about atmosphere. We have two types of the atmosphere. A primary atmosphere of a planet, a secondary atmosphere of a planet. So a primary atmosphere is an atmosphere that formed by accretion of the gaseous matter that is sticky together with the dust during the formation of the planetary embryo. So during the accretion of the disk of the planet Sun, so the gas that is in the what we call the protosolar nebulas. And planets like Jupiter and Saturn have a primary atmosphere. They are generally very thick and dense compared to the atmosphere we have in the telluric or rocky planets, or however you want to call them. Sorry. So classic primary atmosphere is that of Jupiter here. That is composed, of course, from the two major elements that we have in the universe, that is hydrogen and helium. Sorry again. Nitrogen and helium, a little bit of methane, water, and trace elements like ammonia and CO and alkane, mostly derived from UV photolysis of the atmosphere, of the external atmosphere of Jupiter. Of course, the Earth atmosphere is not primary, mostly, because when the Sun starts its nuclear reaction, passes through what is called the Theta stage, called from the name of the famous Theta constellation, where has been observed that when the Sun starts its activity, there are strong stellar winds that strip out all the solar gases, so this primary atmosphere, from the inner part of the solar system. And so we can find this primary atmosphere just in the outer side of the solar system, in the gaseous planets in this case. This is a small cartoon where we can see, we wait a moment, start again. So accretion, bringing volatile, and then this strong stellar wind that strip off the atmosphere through hydrodynamic escape or other processes, and leave only a little bit of hydrogen, as I say, the helium. Helium-3, as I said, is pure solar. The solar ratio of the helium-3O4 is 120 times the atmosphere. In the best preserved rocks on the Earth, we found up to 60. We will never find exactly the solar component because it's always contaminated by air. But it's certainly that the helium have a solar origin. Of course, not helium-4 that is produced presently by the uranium on the crust. A secondary atmosphere is, there are several terminology, is not the one formed during the accretion of the planetesimal, but is an atmosphere, they arrive later, that is formed or by degassing of the planets, by, for example, volcanic activity, or by accumulation of material from impact of other bodies. And this is the two theories that were confronted a long time ago, and I will show you that the people believe that that initially the secondary atmosphere of our planet, it was just degassing of the interior. It's true, but the real source of this volatile comes from outside the space, is not directly coming with the gas accreting with the dust. So this is characteristic of terrestrial planet, which included the Earth, and they generally are thinner compared to the primary atmosphere. So where we can find this secondary atmosphere, we can have an idea of their composition. Just look to the other rocky planets. Venus here, Mars here. This is data from JPL NASA. And this is Mars, the data from Viking and Curiosity 2012. And you see that after 20-30 years between Viking and Curiosity, the results are very similar. And you can see that this secondary atmosphere, primitive secondary atmosphere, are made mainly of CO2, 90 or more percent of CO2, nitrogen around 3-4%, and argon, noble gases, a little bit of water. Here is the same, and with a carbon-nitrogen ratio that is quite similar. He's 18, here is around 25 for these. If you make calculation, it's 22, but it's around 25. It's just I'm looking that I changed this one, it's not changed here. I hope that I'm using the good, but it seems for the moment it looks I'm using the good version of the presentation, but I was changed. I put the error here, 25 plus or minus 5, and what is nice in cosmochemistry that on the Earth, if somebody say me is 18 and the other 25, is chemically different, but in cosmochemistry the difference is very so large that it's when you say 18 and 25 is the same things, is the same source for these two elements. So what about early Earth? Can we know basically what it was the composition without searching in ancient rocks or without making strange calculation or models or whatever? Yeah, we can very simple, roughly calculate what is the early Earth composition. Here we take the present habitable atmosphere that is made for 80% of nitrogen and 20% of oxygen, then argon, and CO2, 400 ppm, 401 I think officially now in the Hawaii Observatory, and water in trace and the other noble gases we discussed before. So this has been manipulated, this atmosphere, by organisms and by the geologic activity. So we can do a very simple exercise. We can take off the oxygen. Oxygen, okay, the small story we tell to the kids at the university or at the school is that at a certain moment, this kind of stromatolite, so cyanobacteria arrive and they start to produce oxygen that is a waste for them and accumulate in the atmosphere. The story is a little bit more complicated because biologists suspected that cyanobacteria, they were much before than 2.5 billion years occurring on Earth. So in reality is a very complicated story where the geological Earth interact with the biology and make this oxygen accumulating finally after 2 billion of evolution in the atmosphere. But just take off the oxygen. And the second things we should do is to rise CO2. Today, CO2 is trapped in carbonates. This is a nice figure Axel should remember, we were together in 2004 in South Africa. This is, you can see here, our giant stromatolite. I am here. I have a mustache at the time, but it's impossible to see. Patricia Corcoran from Western Ontario, as our Archean sedimentologist colleague. This is giant stromatolite. I think it's unique in the world, this so big giant stromatolite. This is the Tumbiana supergroup, if I'm correct. Axel? Transvaal supergroup, yes, sorry. Yeah, Transvaal supergroup at 2.5 is one of the first carbonate platform. So today the CO2 is trapped in carbonates. But before, at the start of the evolution of the Earth, there were no carbonates. So if you take off all this carbonate, you obtain a 40 to 60 bar of pressure of CO2 that is bring back to the atmosphere. So if you make this calculation, then here what you obtain. So I take off the oxygen, I put in CO2, so you see again that, okay, this was corrected, the first one it was not. So you have a similar than Venus and Mars composition, mostly a massive CO2 atmosphere with nitrogen, 2-3%, trace of noble gases, and again a CO-N ratio that is very similar to the other two planets, let's say 25 plus or minus 10. It's possible we will come back later on that were probably methane. This is the theory of Jim Casting in Penn State and the Pavlov, because when the Earth formed, we have the famous problem of the young faint sun paradox. I always forget where to put the adjective. And that means the luminosity was only 70% than the present day. So to maintain habitable temperature, because at the time we have no trace of glaciation, we need a greenhouse atmosphere, so we can do this partially with CO2 or adding methane. But this is another story, and at the end of this presentation we can discuss of this topic. I would like just 3 or 4 slides explain what it was the thinking of the, I have to be careful, there is a philosopher here in the room, what humans think about the original atmosphere is very important, because we stick until the 50s or until the 80s with the idea that all the gas forming the atmosphere and the oceans, it was inside the Earth. It's true, it's just that the source, initial source, is not internal to the Earth, and we will see later on. So we can start with the period of degrees, and so Anaximander is one of the first that suggests that the Earth became like a fluid. Some part of this fluid dry and make the Earth, and some evaporate and became the atmosphere. It's a very simple one. Aristotle is making more complicated the history in his famous Meteorologica. This is the first treatise on the meteorology, and he thinks that earthquake created winds within the Earth, and the volcano was the point where this wind from inside the Earth escaped to the atmosphere. So already started this idea that, of course, through volcanism, we are degassing the interior of the Earth through the atmosphere of the planet. This is a famous painting from Athanasius Kircher on the pyrophylaceous, that is conduit that he believed from the interior of the Earth, where cavity where fluid and gas can up to the surface of the Earth through, again, volcanoes, and so fluids and gas composing the oceans or the atmosphere were bring from the interior to the surface. So this is where ancient people were thinking about the atmosphere. Then we had to arrive to modern times. The first treaty on the original atmosphere of the oceans is William Ruby. He was an American geologist. He was at that time the retiring president of the Geological Society of America. In 1951 wrote these seminal papers on the geological history of seawater, an attempt to state the problem in which he tried to resolve the original atmosphere of the ocean. So in 1950, it's not a long time ago, the people didn't know exactly what was going on and what was real origin of the atmosphere and the oceans. So he had two theories. The first one, that rock weathering, so alteration of rocks, liberate volatiles. And he make a calculation, for example, for water. So if you want to see a weathered soil, here I take a photo from Vietnam, or you saw probably this kind of red soil at Phuket at the airport arriving. With this kind of weather, tropical weather, you have this kind of weathered soil everywhere. Also, if you go outside here, you can see them. And so he make a calculation, but he showed that if we take all the continental crust for 4 billion years and you alter this crust, you can produce less than 100 times less water that is in the oceans. So very few one. And this is even overestimate today calculation, because today we know that when we have to make mass balance about the oceans, we have not only the ocean on the surface, but we have around 5 times more of the equivalent of the oceans inside the mantle. Of course, it's not water, liquid water, is hydroxide, so is present in some mineral as a OH. And this has been confirmed very recently with the discovery in a deep diamonds of the ringwood dye. The ringwood dye, this came the name from Ted Ringwood. This is very famous geophysicist and Australian geophysicist and geochemist. Is some high pressure form of olivine that contain up to 1.5% in weight of water, has been theoretically predicted, has been found in a meteorite in '69, and only 2 years ago, the team of Grant Person in Calgary, that he worked on diamonds to find ringwood dye. So we know that the deep mantle contains a lot of water.
So this water never comes out in the atmosphere?
No. Is stick inside, but only one part has been degassed, but everything's come, of course, from the same reservoir. And also we know that today that the mass of continental crust that we have today, it was not there since the beginning. Starting at the half of the history of the Earth, the 2.5 is model dependent. We have the same volume of the continental crust than today. So we started with a Earth that was most covered by oceans, and the continental crust grew up. So these calculations are very roughly. If today we issue the same calculation, we see that weathering is not truly a process to producing oceans or atmosphere. And so he suggested that, of course, Earth was degassing through volcanism. Again, this idea that all the gas and water was originating inside the Earth and degassed through volcanism. And you can see, this is a picture I take in January in the Argentina, Patagonia, of this volcano erupting. And so people always think that the volcano erupt sulfur because it's smelling sulfur, but if you make a composition of volcanoes emission, is just water and CO2, exactly more or less the composition we have in this kind of atmosphere. So the idea was that the Earth was degassing through the volcanism. This is true, but not the source. This is true. In 1969, Harmon Craig, who is doing geochemistry, know very well Harmon Craig because he did everything in geochemistry, or mostly, of Scripps Institution. He have an oceanographic cruise on the East Pacific rise, And he decided, he had a theory, so the Earth was degassing, and where is the place where Earth should degas mostly is where is most of the volcanism. And the most of the volcanism is not on the continent, is at the center of the oceans, where we have what we call the mid-ocean ridge. There are opening of the crust, and the mantle is directly in contact with the atmosphere or the oceans. In this place we should have the gas. And so what he did, he measured the concentration of anisotopes, the helium-3, because the helium-3 is very poor in the atmosphere, is particularly absent in the oceans, but the helium-3 is very rich in the mantle. What we see here is not the work of Harmon Creek. This is a transect all along the Pacific Oceans. This is North Pole, this is South Pole. This is covering mostly 10,000 kilometers, this transect. And this is a profile of the bottom. And here in red, you have emission of helium-3. And all of helium-3, they are migrating through mostly half of the oceans. And so he detected this anomaly, and he can measure that the amount of primordial gases that were degassing from the mantle to the atmosphere, to the oceans, there was a 4 plus or minus 1 helium-3 atoms per centimeter square per second. This is very important because when you read any kind of volatile, carbon, nitrogen, everything, the flux from the interior of the Earth to the atmosphere is always calibrated against this value. What we measure is the flux of helium-3. And using helium-3, for example, carbon ratio, etc., we can calculate the flux of all these gases. Recently in 2010, with a group of University of Tokyo, we also demonstrated in subduction zone, we have degassing of the interior of the Earth, 20% of the flux we have in the mid-ocean ridge. So the Earth, what is this? This is the remnant of our early catastrophic degassing that took place in the first period of the Earth. So the gas, for some reason, were there and were the gas from the interior to the Earth to the external, but don't mean that they are originally there. So we will come in the next part of the presentation. And we have another tools, again noble gases, that can give us the age when this catastrophic degassing of the Earth took place. So what we have today with the volcanism is the remnant degassing. So the Earth is still degassing a little bit, but most of this volatile has been degassed initially. And this is thanks to the iodine 129, xenon 129 system. This is the first extinct radionuclide discovered and used in geochemistry. Yesterday, Hervé spoke about the hafnium tungsten. This is tools that has been developed. They were predicted before, but the machine to measure them, it's only 10 or 15 years that we have in our laboratories, so we can measure. How it works, this system. Iodine is an extinct radionuclide. His half-life is around 16 million years. That means that after 70 million years, you have no anymore iodine on the Earth. So if you have, and the iodine decay to create 129 xenon. So if in a reservoir you have xenon 129, it means that this reservoir has been formed before the 70 million years, so the period where the parent nuclide was still alive on the Earth, still existing. This is the case. Sorry, this is in French, but I like it. It's from Philippe Sarda's work on La Recherche. I like because it's very simple. Here we have the concentration of xenon 130. Xenon 130 is a primordial noble gas, so it's there since the beginning of the formation of the Earth. And this is what is happening in the mantle. So if you have in the mantle you have xenon 130 here, the time 0, and then you, let's say, time 70 million years or more. So the 130 is the constant. The iodine start to decrease, and here you have the xenon 129 that start to be produced. At a certain point, you have the degassing of the mantle to the atmosphere. You lose a part of 130, 129 that go to the atmosphere. And in fact, today the atmosphere contains 129 xenon. The ratio is this one, 6.5. And then, of course, the 130 stay constant, but the 129, it continues to increase again in the mantle because you still have a little bit of iodine here. And so, in fact, today in the mantle we have a little bit more. The atmosphere is around 8.2. If this degassing happens at the start of the Earth, how will be the 129 xenon 130 on the atmosphere? It will be 0 because with the gas immediately the iodine have no time to decay. Okay, it's not the case. If it's after 70, 100 million years, so the limit. So if you with the gas here at the end, both the mantle and the atmosphere have the same ratio because the iodine has produced everything, while we see here that there is a difference. So using this difference, we can make model and calculate very easily. And so we arrive to the fact that after 50 to 70 million years after the formation of the Earth, the mantle catastrophically degassed, giving the volatile to form the atmosphere and probably the oceans. Okay, why all this story? This is true. And so the people stick with this idea until the 80s, 70s, before we start to do the isotope geochemistry on chondrites. We cannot say really on comets. The first Nobel gas value measuring comets is from Chury this year, Argon 36, in a paper of Bernard Marty and the group of the Rosina team. So the Earth degassing explains how the atmosphere were removed from the Earth interior and concentrated in the atmosphere and probably in the oceans, but do not bring constraint, do not explain what is the source of this volatile. So is this the source internal? It seems not, or is this the source external? And as Nader has explained, the source is external. So let's see how we can trace what is the ultimate source of these atmosphere elements. The reason is that the source should be somewhere else than the Earth, that if the Earth, you try to degas the Earth, nothing should come out from the Earth, because the Earth form here very close to the probably, people say probably not so far from the orbit of Mercury, and then that was the place. I'm not a specialist, so I don't want to receive bad questions from the astronomer model, the make model. And so it's a very dry area of the solar system. So the Earth, once you take off the initial volatile from the of solar composition, it should be completely dry. So here I have the fraction of water in mass for each planetary body on the solar system, and the Earth water content here around 0.1%, and here you have the comets that contain, of course, a lot of water, the CECM, the carbonaceous chondrite, the ordinary chondrite, and the enstatite chondrite. So, yes?
The water content is with respect to what? Is a fraction of what? Of the Earth's
of the Earth mass, for example, or the
total Earth mass.
Yeah.
There's so much water.
Yeah. You have the mass of the Earth is 5×10⁻²⁴ kilograms, and you have 1.4×10⁻21 of the oceans. You had the 5 oceans in the mantle. You make a calculation, you have a 1.6×10⁻³ so logarithm of -3 of the water. So yes, it looks like quite a lot of water, but compare maybe other planetary body, is very poor. You see that mostly of the chondrites contain a lot of water, except from the astatine chondrite. The name comes from astatite, that it is a pyroxene. And this is very dry, 0.001% or something water. So the Earth degassed, but the initial volatile came from elsewhere. And this was the theory that started to explain other phenomena. So the addition of few hydrated bodies during Earth's accretion, this is the new model, like the Morbidelli model, so they arrived very early, and the volatile were segregated from this material. They were partitioned into the magma oceans. They were so in gas inside the Earth, and then the gas again to form the oceans and the atmosphere. This is what we call initially the late Venier model, but now the late Venier is different model, I will show later. The late Venier, it's explained that this body arrived quite late when differentiation was already on. The new model, like the Morbidelli model, explained that we needed this volatile arrive very early on the Earth. I will explain a little bit later with a few diagrams. So, from where come these hydrated bodies? It comes from the outer part of the solar system, and they migrate inside. Yesterday, the presentation we show, another show us some model. Here I have a small animation and come from the Sean Raymond PhD thesis. So here you have the astronomical unit. So here is the Sun, the Earth is here, one astronomical unit. Let's check if Mars have the good size. I'm not sure. I never check about that. I'm a geochemist, so I don't mind. And so external part is there. Here's with eccentricity. The smaller run, you have the million years going on. And so you have this planetesimal that looks at them moving like crazy. And they start to forming planets. So you start with the dry body here in the inner, and with the wet body here, and you will see that during the motion of these planetesimal embryos, slowly the wet bodies migrate from the outer side of the solar system to the inner side. And you will see that these planets change colors. And the Mars looks a little bit smaller than the Earth, but we'll see. You see, you became green and then became blue. The question is, what kind of body? And this has been a big debate in the 80s and 90s. So because you have two best candidates, carbonaceous chondrite here, and of course comets. And still, in the textbooks of the school, you see that it's comets, because comets in the imaginary is just a snowball. Well, it should change our mind a little bit. What is a comet? Fortunately, this is a new challenge. But of course, that if we had to choose between the two, we choose the most rich in water, so comets. But it's not comets, and I will show you using noble gases and hydrogen isotopes that is not the case. So comets, of course, you can have up to 50% of water, and here is the three groups of the carbonaceous chondrite, or Guy Murchison, that is well famous for the amino acid, Allende, that is the one, the most primitive one where has been found the calcium aluminum inclusion that will use to date the solar system, as Hervé showed yesterday. And so you see that the water is between 2 to 20% of in weight. Again, when I speak of water in rocks, it's not a liquid water, it's not a sponge, it's hydrated minerals, so it's a hydroxide, H and O, then recombine on the surface of the Earth to make a real atmosphere and the oceans. Can we just use the ratio of the major volatile? Not really, because when we look, so Venus 18, Mars 25 plus or minus 5, early Earth probably 25 plus or minus 10. You see that solar is different, 5. so solar can be excluded. But the cometary CN, this is I think new measurement done on the Curie, is 21. Chondrite is 36. And again, the error on this estimation is always 20, 30, 40%. So when you say 36, you say 25, from the cosmochemical point of view is the same, so the same source. So we cannot use. So let's use other isotopes, like for example noble gases. This is the case. So here I reported neon 20. This is the abundance of neon 20, argon 36, krypton 84, 130 xenon. They are all primordial noble gases. We suspect some neon, it could be solar, but we come back later if there is some question on it. Here you have a concentration measure on the Martian meteorites for Mars, for the Earth here, chondrites, and comets. Comets is not real measurement. As I said, the first noble gas has been measured 1 year ago by the Rosetta onboard instrument. And this is argon 36. I will show that what it tells argon 36 change all mind, and so it's a new challenge to explain some of what I'm telling you, only one part. So comets concentration is work has been done, experimental work, working on icy reproduction of icy planetesimal at 55 Kelvin, and how noble gas are incorporating this icy planetesimal. Is work done at the University of Hawaii by Tobias Owen and Barnoon. Is a famous paper. And if we look in general, here we reported logarithm of their concentration against the concentration on the sun. So the solar concentration here, the partner will be 0, so will be 1, so the logarithm is 0. And you see that Mars and the Earth have a very similar partner. This is just is a dilution effect, so you have less, and so you have to look at the pattern. The same, the chondrite is the same that Earth and Mars, with the exception of xenon. We have less xenon on Mars and less xenon on the Earth. It's what we call the missing xenon paradox. And then if you look at the comets, the theoretical composition of comets, you have a little bit less the neon than what is expected, a little bit more than krypton, but you have less xenon like on the Earth and on the Mars.
What do you mean a little bit? I mean, for the neon it's 3 orders of magnitude.
I'm sorry, not less in concentration, just the partner is more steepy, but let's say that for the first 3 gases, okay, but this is show that chondrite could be a good candidate. But still we have this problem of xenon. And we spent 20 years in the noble gas community to try to understand where it was this missing xenon. People said it's in the core, because as I said, we can put everything in the core. Xenon and krypton have absorption capacity, so we were suspecting that all the xenon was sticky on the clays on the surface of the Earth. So it was some hidden reservoir. This is not true. One possibility is that the chondrite give most of the noble gas, but if you had a small percentage of the comets, it could explain this xenon deficiencies. In fact, on this experiment, we showed that we have less xenon and more krypton, so the capacity of trapping of xenon and krypton is different on this glaciated surface. So if comets bring part of this volatile, we bring less xenon than how much can bring the carbonaceous chondrite. So if we have a mixing between carbonaceous chondrite and comets, we could explain this missing xenon. But in general, it looks that the other noble gas really looks just diluted, but the same pattern on the chondrite. Looks the major elements here, hydrogen, carbon, and nitrogen is less evident because you see they have a similar pattern, the exception that the comets contain more nitrogen than the Earth's and the chondrite. Here is not report the Mars concentration for these three elements in these figures that I took from. Let's look at the isotopic composition. So here I reported the isotopic composition of hydrogen, carbon, and nitrogen. So here is the per mil of the delta D, so the D on H ratio, the carbon 13, carbon 12 ratio, and the 15 nitrogen, 14 nitrogen ratio. So this is the ratio here, and here I reported for hydrogen, carbon, nitrogen. So if we see here, we see that again the Earth and the chondrite have the closest match, and also isotopic composition of the major elements. Similarly for the noble gases I didn't report. You see here that I didn't report, the author didn't report Mars. We have for Mars, but the problem on Mars, if you plot, it looks like more cometary. But it's not because it's cometary, also if with the new data of Rosetta there is some discussion, is that Mars has been, the atmosphere and the hydrosphere has been affected by hydrodynamic escape. We lose this atmosphere, and so we fractionated the initial ratio. And so we lose more light elements than heavy one, so the 15-14 ratio and the D on H increase and looks like more cometary, but this is because it's an effect of the hydrodynamic escape. And has been demonstrated by the data of Curiosity. They have measured the 36 argon and showed that it's much higher than on the Earth and the other reservoir, solar, etc., because losing the atmosphere, we lose more quickly the 36, the light elements, than the heavy one, and so we increase enormously this ratio. So everything looks like the carbonaceous chondrite could be the good candidate, and this particularly is true for the oceans. So the oceans has been the debate has been resolved using the D on H, so the deuterium-hydrogen ratio of the water molecule, and the temperature favors the loss of deuterium, make water lighter. So reaction between ice and the hydrogen, it makes that in a hotter place you have more hydrogen than deuterium. In colder place of the solar system, you have the D on H that is increasing. You have more deuterium than hydrogen. So we have what is called the heliocentric distribution of the isotopic signature of water. If you go on the sun here, the D on H is 25 × 10⁻⁶. Of course, everything you see about the sun is not because geochemists like us, we went on the sun. We look at Jupiter, we have the same composition of the sun, so it's all measurement coming from the gaseous planet. And the Earth have 154 × 10⁻⁶. This is very precise measurement. The seawater is used like international standard for doing our measurement of deuterium. The carbonaceous chondrite have between 130 and 117 × 10⁻⁶. So you see that the Earth is in between. So carbonaceous chondrite have the same D on H ratio that the oceans on the Earth. And the comets, the few ones that were measured before measuring Chury, but they are mostly comets from the Oort clouds, have a D on H that is very high, so 300, 330 × 10⁻⁶. And if you go interstellar highs, you go up to 2000 × 10⁻⁶. So colder the place, more deuterium rich is the highs of the water. Of course, people are never happy with nothing. We are scientists, so if everybody agree, will be nothing to do in the life. And so the people disagree. This is another way to see. So this is the D on H. The D on H here. measured on in carbonaceous, in micrometeorites here, stratospheric IDP, chondrules and the carbonaceous chondrite, and you see that all this material, the main value of DNH is corresponding to the one of the oceans. Micrometeorites, it's just like smaller carbonaceous chondrite. The composition is the same, basically. And ordinary chondrites have more enriched DNH in the hydrated minerals. And the comets, the sun is here, the comet is here, so the comet is higher, so we could exclude the comets. Of course, people say, yes, but this is Oort clouds, long period comets. The comets that play a role bringing water at the initial of the solar system, they were probably Jupiter family comets. So comets, they were very close inside the solar system, and said nobody never measured them. So that could have the same water with the same signature that the carbonaceous chondrite, that they are not so far in the solar system in the region when they form. And so we will see that thanks to the space mission like Chury, like Rosetta, we finally showed that the DNH on the comets, it seems really completely different from the DNH on water on Earth, so we can exclude the water. Let's come back to, in general, to the volatile. Here is carbon, water, nitrogen, chlorine, bromine, iodine. This is volatile or not atmophile. So the halogens, neon, argon, krypton, and xenon. Here is this is the abundance normalized to the carbonaceous chondrite. Here, if you have the 4% of carbonaceous chondrite to the mass of the Earth, you can explain mostly all the abundance of atmophile elements on the Earth. So you don't need a big masses of carbonaceous chondrite. Just 4% is very small. It's, I think on the moon it is 2% or something, the percentage of this kind of material that have impacted the surface of the moon. So we are in the same order of magnitude. What received the moon received the Earth, probably more, because the gravity of the Earth is more important, so you receive more impactors. This is what will be expected by the late Venier. The late Venier is this theory that says that has been developed to explain the presence of the platinum group elements. Today in the mantle we have a little bit of platinum. This makes happy my wife very much. But what is important is that the platinum should be not there, because platinum elements is the siderophile. They like iron, so they should be all in the core. So if we have a platinum today in the mantle, it means that after the differentiation, some meteorite, like carbonaceous chondrite or other meteorites that are reaching this PGE, impact the Earth and give part, they melt and give part of this platinum group to the mantle. But this is arrived much later. We need already the differentiation of the core, and so if you add the more lead siderophile, the core is formed, the siderophile cannot go nowhere, they just stay in the mantle, everything has been already differentiated. And you cannot explain the amount of water we need before this process. Before this late Venier, very early, we needed this 4% of carbonaceous chondrite coming on the Earth. This is conservative value, of course, because you can imagine impactors arrive, they vaporize, they probably form clouds or that precipitate on the Earth, or they melt the surface on the Earth, and this volatile is partitioned inside the melt. So you lose a lot of volatile. So probably to have this amount, you should maybe have 8% in mass of carbonaceous chondrite, because surely you have lost maybe 50% during the impact. So there is a model explaining as depending the impact angle, you can have a more efficient release of this volatile to the surface than other. I'm not especially, I will not enter on these details. There is two anomalies here, nitrogen and xenon, that cannot be completely explained. Nitrogen is possibly trapped in the core. Finally, something could be trapped in the core. By very recent metal silicate high pressure experiment, Buffet et al. Suggest that maybe nitrogen has been trapped in the core. It's not really new. There were several experiments also in Osaka University where I did my postdoc. We were working on this metal silicate partitioning. The xenon is not enclatrate, sorry, could be trapped on this icy structure. If it will be enclatrate, it will be a higher amount. So xenon could be explained if you had 10% or 20% of cometary volatile, you can explain this famous missing xenon, this lack of xenon that we have on the Earth. It can be explained by just bringing everything with the carbonaceous chondrite. So is this model working? Yes or not? There were several papers that, this is a paper from the group of the museum in Paris that they were asking if asteroid comets at the end is not the same things, that if maybe it's all carbonaceous chondrites. It's one of the big questions they should resolve a theory, but Philae was loose landing, and so we have missing a lot of data on the surface of the comets. Somebody measured in Hartley 2 comets, the D on H, and found that this is a Jupiter family comet that was like ocean-like D on H. So this put again back the debate. And the group of Japanese on the Hokkaido University suggested the hydrogen isotopic ratio in lunar rocks indicated there were more cometary water than the moon, and then 1 year later appeared another paper saying that they were wrong with their data, and they know the lunar was receiving carbonaceous water like the Earth. So the debate went on. And so let's look at, at the end we have Rosetta. So I want to show you a few data of Rosetta. I'm late, so we're already 1 hour 11. So this is very beautiful data. I think it's very exciting data we obtain. Unfortunately, we obtain only from the halo around, thanks to the Rosina. We lose all the data we can have on the composition of this comet. Maybe we will discover it looks like just a carbonaceous chondrite. Why not? It will be interesting. So we hope in one of the next mission, I will probably already retire when it will be the next mission on the comets. It's not only Rosetta. Before Rosetta, we have a Stardust. Stardust show mostly the same things, that for this group of sample, the D on H is a cometary is higher than one on the oceans, but we have a few sample here that looks like ocean-like D on H, but it was suspected that these data were contaminated by the famous aerogel, that is this plastic developed by NASA, so containing hydrogen, that was used to stop this dust particle of the comets, and so we have some contamination of the data. And then we have Rosina, the Rosetta orbiter spectrometer for ion and neutron analysis. There are 2 spectrometer and a pressure gauge. It's quite a complicated instrument that make possible to measure, and this you see here is degassing the comets, measuring noble gases, at least argon, and major elements like carbon, nitrogen, and hydrogen. This we showed yesterday. This is come from the paper of Hartweg. The first thing that was done, it was to measure the DH. It was one of the main objectives of the mission. And you see here the Earth, D on H here, and chondrites, Enceladus, and here you have all the Oort clouds, comets, and the Chury, Jupiter family, again, explain that D on H is too high. So water in the ocean is not coming from the comets at least the water. So what is interesting is that these diagrams is appear in the last paper of the group of Rosina teams and Bernard Marty. Here is a isotope, not really isotope, because we have an element here, plot. You have the DNH here, and here you have the argon-36 that has been measured, the first noble gas measurement direct on a comet, against the water here, carbon here, nitrogen, and again here is report carbon, so this is the carbon. And in this kind of isotopes, let's say isotopes plot, it's rare that you have the mixing line is a straight line, because but it's generally an hyperbola, depending the curvature of this hyperbola of the ratio of the denominator on this. This is not isotope, is elements, but it's the same behavior. So it's depending from the ratio between the two end member denominators. So hydrogen and argon is depending what we are looking for. And this is the expected mixing between the comet, represented here by the measurement, and the bulk Earth here. Here is reported a different model of bulk Earth, taking in the mantle, the depleted mantle, the surface, so it's a different measurement, way to measure, or the bulk total Earth. The ratio of the argon on the water, on the nitrogen and the carbon, and you can calculate the amount of the denominator here that is along this mixing line. And if you take the Earth's surface, this mixing model showed that you cannot have more than 1% of water that came from this type of comets. So if the comets were like Chury, 99% should come from, or the bulk Earth means it's in this case from the carbonaceous chondrite that brought water there. The contribution of carbon here is the same, around 1% or less, it's depending if we look at the Earth's surface. Again, mass balance and the mixing. We have 1% only of carbon, it could be of cometary origin. If we look at the nitrogen, between 1 and 10% of nitrogen could be of cometary origin. Again, 90% it come from another source, so the carbonaceous chondrite. But we can calculate also on this mixing what is the percentage of carbon. This here is in the denominator. Of course, we can automatically calculate what is also the percentage of argon-36 in this mixing. And what is come out that the argon-36, at 99%, it could be cometary. And this is start to be trouble because, well, we say that looks everything's come from carbonaceous chondrite, but the one of the ever noble gas, argon, it could be cometary. So this first paper, there will be a lot of debate, but what it suggests this is that if argon, that is one of the ever noble gases, bring from cometary, maybe we can assume that also krypton xenon come from comets, and this will explain this famous mixing xenon. So comets bring a little bit water and could bring also the heavy noble gas. But this is just the start. We don't know. So it's a new challenge to try and explain why one of the noble gases that we expect should be of carbonaceous chondrite origin. We saw before the concentration, so it looks like chondrite. It seems from this mixing model that at 99% it's argon, it's cometary.
Yeah. What's the difference between the two plots?
Just is here is exactly the same. Just here we calculate along the line the percentage of the mixing of carbon, and here what is the percentage of the argon-36 in the same mixing. It's only this, but exactly the same. This area is different because we're changing the species, is nitrogen, so exactly the same, but we can calculate, of course, mass balance the percentage of the two. So I make a small model. I have a few minutes again. So what could be the general model of the formation? So you see, I'm not very good in it. So let's make, fortunately we don't have people making model of how we form planets. So as the planetesimal is coming together, so we have time 0 plus 30 to 70 million years is what we expect the Earth is creating a form completely. Is in this time lapse. We don't know. It's depending what extinct radionuclides you use. Has been proposed also the planet like Earth, it could be formed in 10 or 20 millions only. You have a primary atmosphere solar composition. Then you have the Theta stage. You strip off the, here it should be a tenuous atmosphere, but we cannot see. And you leave helium-3, maybe a little bit of hydrogen. So the helium-3 that is a solar composition and nothing more. You see that the planet is not differentiated yet. And then you have the wet asteroid. Very beautiful, I just passed a copy from internet. And maybe of the Vesta families, the next Osiris-Rex maybe mission, we could give some clues about what is the best family of asteroids, could be the best candidate of this kind of carbonaceous chondrite. So if Bennu type asteroid, it could be one. And so you had the neon, the nitrogen, the argon, and, the neon, the nitrogen, the carbon, and water. Okay? And then maybe you have a few comets, the Jupiter family, and this maybe could bring the heavy noble gas, argon, krypton, xenon, if it's true this what has been measured at Curie. So the heavy noble gas, it could be of cometary origin. But again, I say there's really some new data, and then we need to really have more information and more data to conclude about that, and possibly a little bit of water of cometary origin. Mass calculations say that you cannot have more than 10%. In the best 20% of cometary water, everything has been brought by the carbonaceous chondrite. Then what is going on? You start differentiation, and you have magma ocean, maybe period. Magma ocean could be also much earlier. We will see with other cartoon if I have, I still have time, 15 minutes, about the oceans. Maybe there's some big impact, like the famous Mars-like sides Theia impact that could have melted all the surface of the planets. And so you are partitioning volatiles in the melts, so they are bringing inside the mantle, maybe in the core for nitrogen, to explain these deficiencies of nitrogen. And then accretions is terminated, you start to degas catastrophically for some reason. So maybe the Theia impact could explain why we have this catastrophic degassing. At a time between 50-70 million years after the Earth formation is the iodine xenon model that predicted that in this time lapse we should have this catastrophic degassing, and most of volatile come back to the surface, created the atmosphere and possibly water. Part of the water still is in the mantle. And then this is differentiated Earth. You have your late veneer bringing a little bit of PGE, but this is another story, as I said, except my wife not busy in his interest on platinum elements, is another story. What it was the early atmosphere? So this we could stay here at 3 hours, but Carlos had to speak about biology. So it's likely that from early times, what has been rejected by the mantle, which has been degassed by the mantle, is oxided species like nitrogen, CO2, because Comatite, that is one of the ancient lavas that exists on Earth. Hervé spoke yesterday. If you look at the mineral assemblage of the comatite, you can calculate the oxygen fugacities. You can calculate the radiostate of the mantle. And the radiostate of the mantle, at least at 3.5, we don't have comatite older than that, show that the mantle, at least at 3.5 billion years, it was already oxide. It was in the fire-light, magnetite, quartz buffer. So what is emitted through volcanism is oxided species, CO2 and 2. So this is exactly contrary of what is needed Miller to do his experiment. They use reduced species. But of course, this is 3.5 billion. If we can find comatite older than 4 billion years, maybe we can check if at 4 billion years, mantle was oxided like 3.5 billion. It was rich in CO2, so a recent work done by several groups in 3.5 billion years Australian rocks suggests that we have around 1 bar of nitrogen and probably 0.7 bars of CO2 still at 3.5 billion years. Possibly methane, this is the model of gene casting, to explain how keep warm the temperature on the surface of the Earth with a 70% only luminosity of the sun. So we need some kind of greenhouse effect to explain, to keep the surface of the Earth stable at normal temperature and not a freezing temperature. So what happened with the oceans? So Muriel will be happy. You remember, it's our first big paper and Origin of the Oceans, 2005 on Springer, this cartoon. Why this is good, why my previous cartoon are bad? Because this is a professional designer that did. So I just arrive, I make it like before. I needed something like this, I need a big impact, something. She did a very good job. So this is based on the model Mossillo's Leap and Tal. So the suggestion is that maybe the catastrophic degassing has been triggered by this famous impact expected with this Theia, this planetoid of the Mars sides, and that melt all the surface, and then it's following the model of Leap. All the water CO2 has been degassed outside, and even the gas forming an atmosphere very rich in water. If you take all the water of the oceans, you put in the atmosphere, you can reach around 220 bars of pressure. And if you take the 40 bar, you can add the 40 bar of CO2. In the model Sleep, he calculated also if we extract also all the carbon that is in the mantle, you can arrive to a crazy pressure of 480 bars. This is just model. And some clouds of silicates, droplets of silicates around the Earth. So this impact is happening around, again, 50 million years. It seems everything's happened 50 million years. We have no yet the resolution to separate all these episodes. So we have this greenhouse Venus-like Earth. And the question is why Earth survived and the change to the Venus-like to Earth-like. Venus, no. The model of Sleep suggests that in a few millions we create, a thick basaltic crust that diminish the heat flux from the interior of the planets, and without the support of this heat flux from the internal part of the planets, the greenhouse cannot sustain more than 100,000 years or 2.5 billion years. Is again model independent. So you isolate the heat from the interior to the external part, and this greenhouse at a certain moment start to collapse, and so it can we can decrease the temperature at the surface of the Earth, and we have condensation. Condensation could have happened at high temperature because still we have a high pressure, so it's just the diagram of water, so we don't need it to be a 1 bar, also a 50 or 100 bars. You can, or something, you could have a condensation if you have high temperature. And how much it takes, we don't know. Again, is temperature dependent. What I put here is this age that I put is the age of this famous zircon. They say that it was a liquid water on the Earth. So the upper limit is the 4.4, and 4.26 is where the majority of this zircon show the age. So that is maybe the most sure at the lower limit. So somewhere around here, water starts to condensate to be stable. And then the problem is that how we can decrease, you said before, so how we can decrease the CO2 at the start, maybe it was dominantly CO2, we showed the early Earth maybe could have 90% of CO2. We had to decrease this amount of CO2, this is too high, and one idea is that between this age here, 4.3 and 3.9, 4 billion years, at the start of the Archean area, maybe we have some kind of plate tectonics, and so we have weathering of basalt. So when you alter basalt, what is happening is that you produce carbonates, and the carbonates could have been recycled through the subduction zone in the mantle. So you extract the CO2 from the atmosphere and you put this CO2 back to the mantle. And so you decrease the amount to few bars, and you start to have a condition more likely for life. Still, so this is an artistic view that as it could be expected, the idea on Earth. Small continents and the global oceans. What it was the chemistry, so in one slide, and was the temperature exceeder. So reaction of this seawater at high temperature with a sodic basaltic crust. The basalt contains a lot of sodium through plagioclase. It promotes salinity formation, so we have brines. There are few fluid inclusion studies on the Archean rocks that suggest a salinity between 1 to 2 the salinity of today. So 35 to 70 weight% of salinity. What it was the temperature at that time? So this is a big issue. It was proposed using the oxygen isotopes, that the temperature at that time were very high, like 100 degrees. Today we use 2 types of isotopes, the oxygen isotopes and the silica isotopes in chert, that is a kind of microcrystalline silica. When you have exchange between seawater and chert, you exchange the oxygen and you have isotopic fractionation. This isotopic fractionation is temperature dependent, and the silica is a little bit more complicated, the system, but again you have precipitation of silica that is temperature dependent, and through the isotopes of silica you can calculate, and both models suggest that at the end times the temperature could be high as 50 to 80 degrees. We can discuss later if you...
Water?
The water temperature. So...
You mean arcane? You said Hadid.
Centigrade, Celsius.
No,
sorry.
You said Hadid. Did you mean arcane?
Well, the data we have, the rocks is Archean, because again, the rocks is 3.5, 3.8, and the oldest rocks. So at the end, we don't know, because again, after 4 billions, we don't have. So, take-home message. So, the atmosphere, hydrosphere on Earth, it seems to have a common origin. This wet planetary body, like asteroids, few asteroids of carbonaceous chondrite, will be interesting to see what is the result of the next mission I don't know when, I think he's taking a sample and bring him back, Osiris Rex, but it's probably in the room we will be more or less, except the young student here retired, so I don't know if we will participate to the missions. Contribution of cometary volatile, sorry, it seems is minimal, except maybe for every noble gas. As I said, Rosetta brings new data, very interesting. So it's challenging again a little bit all this theory. So we need to go on this kind of mission. And also if we have a liquid water and atmosphere at the start of the Archean, it was maybe quite hot and quite saline. So this limits a lot of the type of organisms can develop. Just thermophile maybe, or halophile. So extremophile. So well, I will leave biologists maybe make a comments on that. And so while some people is enjoying Vietnam, as I will show in the next figure, I ask you if you have a question. And thank you for your attention.